Good afternoon. My name is Nick Southall. I'm a Senior Project Manager with cbec Eco-Engineering, and I'm here with you today to share our work on filling the salmonid rearing habitat deficit on the Lower American River in California. I'm accompanied in this work by my colleagues Chris Hammersmark and Michael Founds. Joe Mers with Kramer Fish Sciences supported this work, and also Rocco Brown and Lily Allen and Tom Goring with the Water Forum. So no doubt the audience here is full of scientists, engineers, ecologists, geomorphologists, hydrologists, modelers, and many other disciplines. And with all these tools at our disposal, how do we effectively integrate the physical, ecological, and economic metrics to inform social restoration decision-making? I'd like to start with giving you a little background before explaining the history of spawning projects on the Lower American River, and then walk you through the different tools that we employed to assess and prioritize the rearing habitat opportunities. So firstly, a little bit about the system that we've been working on. The Lower American River, not a pristine river. The Anthropocene is alive and well here. California's Central Valley was once a stronghold for salmon, and the California Gold Rush, settlement of and agricultural development of the West, the urbanization of Sacramento, and the damming of nearly all the Central Valley's rivers have led to major declines in native salmon populations. In the 1950s, Folsom and Nimbus Dam were constructed largely for flood control, but also for hydroelectricity, irrigation, and municipal water supply. They also, of course, created a fish passage barrier, regulated flows, and interrupted natural downstream processes and floodplain processes, and of course limited anadromy to the lower 23 miles of the river. It's clear that we're working in a highly modified system. The keystone species in the Lower American River are four-run Chinook and steelhead. Four-run Chinook are the most widely distributed run of Chinook salmon in the Central Valley and with a target population for our work. The Lower American River produces 20% of the Sacramento River's fall run Chinook population, and so are an important species for recovery. The life history stage of interest was the juvenile rearing period from January to June, after the fish have moved into the river and spawned, immigrated and spawned, and then the eggs have incubated over the winter months. A brief history of the work on the Lower American River. The Central Valley Project Improvement Act of 1992 set an anadromous fish restoration program doubling goal for four-run Chinook salmon of 160,000 natural spawning fish. The Bureau of Reclamation provided mitigation dollars for the impacts to anadromy in interruption of the downstream sediment transport and starving of the gravel beds that are required for spawning. This was believed to be a primary limiting factor in fish population, in the growth of the fish population. In 2008, a multi-year gravel augmentation and floodplain enhancement initiative was implemented. And over the last 12 years, the focus of recovery efforts have been on gravel augmentation efforts to improve spawning conditions. As side channel and edge habitat was already present, it was thought that rearing habitat, although limited, was not the primary limiting factor. Since 2008, cbec and our partners have designed and implemented 9 successful gravel augmentation projects and some associated side channel projects on the 23-mile reach of the Lower American. This figure here shows the distribution of those projects, largely in the upper half of this reach. At the right, you'll notice Nimbus Dam. To the lower left is the mid left is the confluence of the confluence of the Lower American with the Sacramento River. And the Sacramento River then flows south from here towards its confluence with San Francisco Bay and ultimately out to the Pacific Ocean. The image on the lower right there is one of the gravel augmentation projects occurring at one of these sites. So Central Valley salmonid populations continue to be depressed. And in the last 10 years, the conversation has shifted and evolved to acknowledge that in order to achieve the doubling goal, in addition to spawning habitat, there also needs to be the creation and availability of rearing habitat. So the first question is, how do we approach this? How do we answer this question? So a key question for decision makers is how much rearing habitat is needed. And the first model that we looked at, just move my window here a little so you can see it. The first model that we looked at is the Ishi model, Emigrating Salmonid Habitat Estimation Model, that was developed by our colleagues at Kramer Fish Sciences. This model looks at fecundity, survival, and migration rates, and estimates how much floodplain and side channel rearing habitat is needed to sustain these target abundance levels. If the model is loaded with 160,000 natural spawners, it identifies the spatial and temporal habitat requirements to support this target population. In a medium scenario, shown on the images on the right there, approximately 500 acres or 200 hectares of rearing habitat is needed to support that population. In a typical salmonid spawning season flow of February, March, we see about 3,000 CFS in the river. And we know from our flow modeling work and habitat suitability that currently approximately only 100 acres of good quality rearing habitat currently exists. So this identifies a clear habitat deficit for rearing and then fuels our work for habitat identification and prioritization. So knowing the deficit, we set about identifying and prioritizing rearing habitat opportunities. We began with a review of the physical and discharge data for the river. And within this data, using this data, we conducted hydraulic and ecological modeling, and finally undertook a data-driven method to weight and rank opportunities through an evaluation of the project cost and their ecological uplift. In 2017, a full bathymetric and 1 meter resolution green LiDAR survey of the river was completed, resulting in full topography for the 23 miles of the river, of the lower river. For physical geographers in the audience, such as myself, I think this is a pretty interesting piece of work. When applying flows to that, we could review height above river, and using a base flow that was selected of 2,000 CFS, begin to identify rearing habitat opportunities that exist on the floodplain. In addition to this, we also conducted a visual assessment. Many of the tools that we employed, the model, the topography work, the GIS analysis, only take you so far. And I think it's worth noting that there's also a visual assessment that can be needed by somebody in the industry. Perhaps this is the craft of eco-engineering and river restoration, river enhancement, that allows additional opportunities to be identified that maybe some of the other tools didn't pick up. And it's also worth noting that we looked at existing vegetation cover on the floodplain, obviously wanting to be aware of existing good quality riparian habitat, and also identify open areas, both for restoration and for revegetation. Combining the topographic surface with discharge data, a two-dimensional hydrodynamic model of the 23-mile reach was developed, which should be exciting for all you modelers in the audience. And this resulted in a two-dimensional hydrodynamic model that we combined with habitat suitability indices to estimate the spatial distribution of existing rearing habitat. It's important to note that we wanted to understand where existing areas of high quality habitat existed, also to replicate those conditions that were present on the river, but also to do no harm and be careful not to damage areas of good quality habitat that currently exist. So to look for the optimum conditions for salmon, you obviously look, on juvenile rearing, you want shallow depths, you want slow velocities, and that gives you a habitat suitability indices. And we also applied cover to that variable as well, given the needs for floodplain roughness and the food web inputs that riparian or flooded riparian areas can provide. So this created a cover habitat suitability indices. And the image on the right there showing a flow of 10,000 CFS. The blue selection on the graphic shows those areas of floodplain downstream of bar forms and islands where high quality habitat currently exists. So we were looking to not only enhance those areas, but also taking care not to damage areas of good quality habitat that are currently present. Our initial prioritization efforts looking at these elements identified 55 potential sites throughout the river corridor. These varied in terms of opportunity type and often overlapped, such as in the case of side channel creation with associated floodplain grading and revegetation. To refine our focus, we dropped the less viable opportunities, and this was based on a preliminary assessment of project cost and the potential for habitat gain. The right-hand lower image there shows the 33 sites that were retained for further investigation. To identify and determine our project costs, it was important to us to refine the project footprints. And we also wanted to come up with a standardized methodology that we'd apply to all sites. It's easy to introduce bias. And so we wanted to have a thorough method that could be objectively applied to all of these opportunities. For this work, the grading footprints were limited to 10 feet above the base flow of 2,000 CFS. We wanted to do that because higher floodplain areas obviously result in higher grading costs, and they become the habitat efficiency, the cost for restoration climbs quite quickly once you get into those elevations. As we mentioned cover previously, we wanted to minimize disturbance to existing mature riparian cover and carefully locate these, in the case of the image on the left, the channel locations to avoid areas of high quality existing riparian woodland. And we also wanted to acknowledge that the channel grading boundaries, despite our best intents to want to carefully drive a backhoe through these floodplain areas, to borrow a phrase from our colleague John Hannon, these side channels and alcoves are going to have an associated footprint. And it's important to think about the grading that would be associated with them and the footprint of disturbance so that we can accurately develop a total project acreage. So from these 33 sites, the refined grading footprints, we identified approximately 284 acres of rearing habitat potential. By far the greatest of these was the cut and revegetation. We termed these habitat treatment types. And this would be the lowering of an existing floodplain to increase the frequency of inundation, and also the revegetation of that surface for the cover that provides, the refuge, the lower hydraulic velocities, and also for the macrophytal food sources that you know, a vegetation covered floodplain can provide. Applying the economic lens, we determined the initial construction costs. The material volumes were used to generate the grading costs. We looked at the cost of grubbing and local haul, and then we also looked at local reference project to develop revegetation costs to get an accurate estimate of what would it take to revegetate these areas of floodplain that we'd lowered. The bottom image there is from our preliminary evaluation, which shows the potential cost of these projects against the habitat gain that we perceived could be delivered from each site. And finally, to the quantification of ecological uplift, another important parameter in this work. It's important to notice that an acre of habitat created does not accurately reflect that habitat function at varying flows and across all sites. The habitat suitability of potential rearing sites was modeled against flow records to arrive at weighted usable area. And the graph at the right there shows that each site has a unique WUA, weighted usable area flow curve. And from the image, the little graph on the right, which my camera is obstructing, you can see that as flows increase, the suitable acres of habitat also increase in this graph to 15,000 CFS, where the suitable acreage is at its maximum before declining as floodplains get further inundated and habitat becomes less available. There is some debate in our industry about whether seasonally inundated floodplains or perennial side channels provide a greater rearing habitat opportunity for juvenile salmonids. In order to address this question, we use the acre-day approach. The weighted usable area calculator evaluated the available annual acre days of habitat over the rearing period, and we looked at daily flow records from 2006 to 2019. This is the currently managed flow regime from the upstream reservoirs. The calculations compared project footprints under existing conditions and also proposed conditions, proposed designs, based off an analog conditions that we found in the river. This work creates a multiplier. So for habitat, 1 acre of floodplain habitat that's created, we determined that this creates approximately 26 acre days per acre of habitat during the rearing period. So for floodplain areas, these are potentially large areas, large footprints, however, are not always inundated, as the graph on the right there indicates. Excuse me. Versus the side channel scenario in the bottom graph and tabular graph there, that shows that for a side channel, the multiplier would be 41 acre days per acre of habitat created. So while there's a greater multiplier and temporal benefit, it's also over a smaller project footprint. So from this work, looking at the physical, economical, and ecological aspects of our project work, we can then report out on these project sites objectively. In the case of this site, number 27 near Sunrise, we were able to say that the existing habitat use was 24 acre days. The future habitat was 341 acre days, which gives us a gain of 317 acre days of habitat, usable habitat for rearing, if this site was developed. The grading volume, 96,000 cubic yards associated with the side channel enhancement and floodplain grading. The cost was approximately 2.2 million, which gives us a cost per acre day for that habitat of close to $7,000. And that's an important metric to consider when ranking these project sites. And lastly, the site ranking for this one. It's a 12.4 acre site. It came midway through 33 sites that we pursued for further development. So this approach gives us a objective mechanism to quantify and a cost-effective approach to identify and prioritize the fall Chinook rearing opportunities. It's a starting point for informed discussion with stakeholders, and then you introduce the social restoration decision-making. The next steps were to meet with stakeholders, refine the leading sites, and also prioritize those opportunities that we wanted to advance for further design and ultimately implementation. Through the use of these physical, economic, and ecological tools, we can inform the prioritization for restoration projects. This has been interesting and exciting work. I'd like to thank our supporters for this work. Move my window again. The Fish and Wildlife Service, the Bureau of Reclamation, Kramer Fish Sciences for their support with their fisheries biology, and of course the Water Forum, our client. Many thanks. Look forward to hearing from others who've done similar prioritization initiatives, and thank you all.